All right. Well, thanks very much for coming in. And no one's logged on, but we'll record this so that if students want to replay it and look at the videos, they can to improve, to help their study. We're going to operate this, I want to operate this system while you're on study leave. So whenever we have mathematics scheduled, I should be at the room ready to help any of the students. So I'll use the math schedule unless I've been asked to cover a class. Then I won't be able to do that. So let's move forward and look at the first. If I can move this slide. All right, the first topic is moments of a force, and I'll ask you to, if you could for me, that would be really appreciated. We'll just video the first segment, and so we can sit there and video. Thank you. Okay, so the first subject is moments of a force. And so the learning objective of moments of a force is understanding what is a moment of a force. And we're going to, that's the turning effect. If you were to take an object and move it, that's momentum. That's the moment of a force. So we'll move it and we can apply force from a certain direction. So we've got an object. If I push that from the center of gravity, it will rotate. Now, if I push it there, it rotates anticlockwise. If I pushed it here, it rotates clockwise. If I push it here, it rotates anticlockwise. So this is the moment of a force. So we'll look at the learning objective is to be able to calculate whether there is a clockwise or an anticlockwise. Moment of force and how that's worked there. Now what we're going to be doing is it's going to be the force multiplied by the distance that force is from the object. So we're going to have an object and we'll consider it the center of gravity of that object. And if we push that object at a point away from the center of gravity, then it's the force times the distance, and that's going to be in Newton meters, that's the units. So we're going to have an object. We're going to just say that that's the center of gravity. And we're going to put a force in this direction at this distance away from, let's call it a 10 Newton force. And let's call it 2 meters from the object. Now this distance is from the object, perpendicular distance, is the distance we use. So the moment will be 10 newtons times 2 meters, and that is 20 Newton meters. And you can see that it is going to be, this is going to push it anticlockwise. We're off the screen for that. Right. So what we'll do is just also, while you can carry on, have you done one already? Have you? Okay. You can do another one now. We're just going to do a second one very shortly. The other type of situation is when you've got an object and we are applying it at a direction which is we don't know the direct distance, but we do know that it is, say, we understand that length there to be, say, 8 meters. So we may not know the perpendicular distance, but we do know that to get to that force, it's applied here at 45 degrees at an angle from the object, and it's 8 meters away where it's applied. So if we apply a force here of 10 newtons, now we don't multiply by 8. We have to take that force, we keep it going, and we find the perpendicular distance that that force is away from the object. We have to know that length here. And using angle, the opposite, and hypotenuse, this will be 8 sine 45. And now we can find the moment of this force is 10 newtons times, not 8, but 8 sine of 45. That is the perpendicular distance, not the distance it is at an angle. And that is in Newton meters, clockwise or anti-clockwise. So this force is going to cause it to rotate again anti-clockwise. Good. Thank you. There's a few slides. There's a few slides on the textbooks that I've used. Have you got a textbook here? Use this. Now I've taken a few questions from the textbook for each section, and we're just going to look now at 2 questions, and this is on page 119, question 7. Have you got your calculator? And we'll just look at question 7 and question 9. Now both of these questions we don't know the perpendicular distance. We have a 6 Newton force. Alright, let's just have a look at that one. 6 newtons, 45 degrees, 7.2. So I'll just clear this.
So have you repeated this as well?
No, it's alright. I really just want that information. They will listen to the solution and they won't get to see it, so that's fine. We've got a point, we've got a 6 Newton force, and we're told that there's an angle here of 45 degrees. And this distance away at 45 degrees is 7.2 meters. Now that's like saying, there's the object, but we're going to apply a force here, in that direction, of 6 newtons. And this isn't attached to this object, that's just the centre of gravity, that's how far it is away from everything revolves around the centre of gravity. So we're going to find this perpendicular distance here, which is hypotenuse opposite, so the opposite equals the hypotenuse times sine of 45. So that's the distance. So the moment of the force is 6 times 7.2 sine of 45. Actually calculate set on degrees. And
So it's 36.7.
you've got, I'll just so you move alright. So here, 7 times 7.2 sine of 45. What did you say?
36.7.
36.75. Now see, you'll see the little R on the calculator?
Yeah.
That means it's radians. So the three significant figures, we'll just say it's 30. We've got 30.547, 547, 01295. That's the calculator version, so we're going to say 30.5.
So how could I be going clockwise and anti-clockwise?
So let's have a look at this one. There it is. If you push it in this direction, it's going to turn. It's going to cause it to turn. So all you have to do is imagine the object is here, and then pull it here. So there's the object. Pull that here. What's happening? Anti-clockwise. All right. Let's look at the next one now. This next one is 9.5 newtons. And it's 2.8 meters away from the object at an angle. They've got a 60-degree angle. Oh, hang on. Looking at number... Oh, yes, number 9, yes. What was that beep? Let's see if I can put the solution on here. So now we've got a distance, it's 2.8. Now, keep in mind now, where the angle is, be careful. So we've got a force point, and we're told that's 60 here, and this length is 2.8. Now we want to know this distance here. How do you calculate this distance here?
Yeah.
What did you say?
One.
No, but how did you calculate it?
I used cos.
Good. Well done. So the adjacent side, so it's 2.8 cos of 60, and then you multiply it by the force. So let's just put that on the computer here. We've got the adjacent side. So it's 2, I'm not the best at writing, using a mouse, 2.8, that's cos, C-O-S, and 60 degrees. All right, and what is 2.8 cos 60? The sine of 30 is a half, and cos of 60 must be the same as sine of 30 because the angles add up to 90 degrees. So cos of 60 is a half, times 2.8 is 1.4. So the result of the moment of the force is 9.5 multiplied by? Oh, great handwriting here. 1.4. And what's that answer?
13.3.
Say again?
13.3.
9.5 times 1.4. Oh, 13.3 is correct. Okay, good. 9 point, I thought it said 30. 1.4 and 13.3 is correct. And the units? Must put 13.3 and capital N for Newton and little m for meters. And what direction is it?
So it's clockwise.
Huh? It is clockwise because that force is going to cause it to go clockwise. So we'll put CL. Good. All right, so that's the end of the first module for today's session, the moment of a force acting on a body. What we're going to do, the next topic is we're going to look at finding the sum of moments of a force. Okay, the next section is finding the sum of these moments. Now, we just looked at one moment of a force. And what happens is, learning out from here, finding the sum moments of a force. It is possible to apply more than one moment. And so what we just looked at is there was one force, then there was another force. If we take, for example, one of our, the first one we had a force of, what was it, 6? 10. What was that first question? I'll just go back. It was 6 newtons, and we had it going up here, and it gave us a clockwise of, what was our Newton meters? 30.5? And that was anti-clockwise, yeah? Yeah. There was the second question, there was a force somewhere, it was down here, like this. And that was a force of 9.5 meters. That's a 60. Now that times the distance gave us 30.5. 9 times the distance gave us 13.3. This is clockwise. That will cause a moment of 13.3 clockwise. This causes a 30.5 millimeters of anti-clockwise. So what do you think will happen here?
So we add the...
Yeah, well, they oppose each other. So they're not both adding. We look for the largest force. Which one will win? What we could do is we could call that one, if you like, the positive direction, because anti-clockwise is the positive angle. We could call that the clockwise the negative direction if you want to know, add all the clockwise. Add all the anti-clockwise together. And then find which one's the largest. This one is greater. Therefore, the overall result will be 30.5 newton meters minus 13.3 newton meters. And we'll have a result of, what's that? No. 17.2 in one direction. That's anti-clockwise. This is clockwise. It will be anti-clockwise because that was the greater force. And so this will counter some of the force. It will slow down. It will cause it not to move as fast. That force, remember, we're talking about turning it. All right, so what we can also look at is the fact that, and I think now we're going to be looking at also vertical. Remember from the last sections, the verticals and the horizontal. If it's in equilibrium, the verticals will equal the horizontals. So we can still use that concept, but we're going to now look at a force where we can take points and we can see this is if it's at rest. It won't always be at rest. Let's take a situation, first example, we've got a point, we've got a line, and what we get in from the end, there's a force acting down of 3 meters. Now that could be, is it a light rod? Force is acting on a light rod. If it's a light rod, it means do not consider the mass of the rod. The mass usually acts, if it's uniform, it will act directly in the center. So there is no force acting directly in the center. So there's only a 3 meters. Hello. Good morning. just onto the second topic, the first one you catch. Now we've also got this, we're recording it also for students who didn't show up, so they can look at they can't see the web, they won't see the board, they'll only hear. If they wanted to see it, they could have logged on, but it's difficult for everyone to sort of log on. We're just looking at the moments of the course. The learning objective here is looking at the sum of moments. Just to revise briefly for your benefit. We have a body, that's the center of gravity. We call this some object. And at a certain distance away from that object, hello.
How are you? How did you come? Early morning?
Very early. Long time.
The 6 o'clock?
Yeah.
Let's start with dialogue at 7:30.
Oh yeah, well I didn't consider that. What happens is if you have an object and we apply force at a certain distance away, there's the center of gravity. If we push it here, the center of gravity is there. It's going to turn, and that turning effect is called a moment of the force. So the moment of the force is its turning effect, and there's a force pushing it at a certain distance away from the center of gravity. So the force is newtons, and the distance is meters. So the formula for moment is the force times the distance, and the units is going to be newtons. So what we've got is this 6 newtons, that must have been 5. Was it 5? 6 and it must have been close to 5. This distance is about 5 meters. So 6 times 5 is about 30. It wasn't exactly, we had to calculate it. This, we were told here, we were told that distance, and we had to, I think that distance was 2.8. 2.8. We had to multiply because the adjacent side, we had to multiply that by cos of 60 to get the distance. We always go to the right angle distance, not the distance. So once we've got that force, we've got one force pushing it, what's called anticlockwise. We've got another force pushing it clockwise. So this force down here pushes it this way, and this force pushes it that way. And so because we've got two forces, the greater force is the anticlockwise force. So we subtract the clockwise force. And so the result is the overall moment of the force. And it says it will eventually, it's an anticlockwise turning effect. So what we're just looking at now, we were talking about a light rod. A light rod means you do not consider the mass, which is usually acting through the centre of the rod, if it's a uniform rod. But there is a force here of 3 newtons acting 1 metre away from the end point, which is called P. And I'm just looking at on page 121. And then there's another force 2 metres acting up, 2 newtons acting up, and 3 metres from here. When they put 3 metres, that's 3 metres, they put both, one's on top, they're both on top. 1 metre here to that point, and then 3 metres from that point to that point. So 4 metres all up from here to here, so you have to add those. Now what we're going to do is, this force would cause clockwise turning effect. This force would cause anti-clockwise, and we're going to find out what is the overall result. So let's look at the clockwise is, now I like to use positives and negatives. I think we'll just consider clockwise and anti-clockwise at the moment. The clockwise is force times distance. Newtons times the distance away, 1, is 3 metres in the clockwise. This force here is an anti-clockwise force, and it's how far away is it? The force is 2 newtons, and the distance is 4. That has an 8 newton meter in the anti-clockwise. It's only 2. This is 3, but because it's much closer, it doesn't have as much leverage effect. This has got a greater leverage. So the stronger one is 8, so we're going to say 8 newton meters in the anti-clockwise is greater. Take away the smaller one, and we've got 5 newton meters. And we took moments, we took the moments about that point. And we can take moments about any point, but we were instructed initially which ones to take moments about. Okay, so let's do an example. Let's do an example which is in your book on the top of page 122, and it's question 1F. So I'll give you a moment. So, pardon the pun. Have you got a textbook? All right, you'll have to rearrange the seating. Can we put a table? Can we do this? I can move. I can't move this. I'm going to have to ask you to move over here, perhaps. I thought I'd be talking to myself because I was going to go ahead and talk to the computer somewhere else. Thank you very much for actually taking the time out of your holidays to come in. This is how we're going to operate in the study leave. Study leave, I'm going to have, if you're normally scheduled on at a particular time of the week, even though you're at home, I'm going to sit here in the room, and I won't move it because it's only, we can have a webcam. If you've got a webcam, I don't need to see you. But you'll be able to see me, and I'll be able to see who's online at the moment. There is, if I use my glasses, I can see who's online. One, that's me. Yeah, I'm online. But we will, I will let you know by email the topic, and if there's any requests, then throw a request. And if there's any other questions, we can do that later after the session. But I'll break it up into like 15-minute topics, like this one is only 15-minute topics. All right, so let me give you the chance to do this question. This time P is at a point in the center, it's not on the end. So you've got to go from P, the distance from P each time. You've got which forces, you've got to know, is it a clockwise force or is it an anti-clockwise force? So let's look at the first one, 3 newtons. What do you think? Anti-clockwise or clockwise? It's anti-clockwise, good. So you just have to do force times that distance away. Good. So you've said the first one is anti-clockwise. Anti-clockwise. And the distance is 2 meters. 3 times 2 is 6. So the 2 newtons is a clockwise, and how far is it? What's the distance from the point? 1 metre. So it's 2 times 1, and that gives us a 2 newton metre moment, okay? Clockwise. The 1 newton is a clockwise, and its distance is from the point. Let's call them taking moments about point. Taking moments about point. 1 times 1. 1 newton metre. And finally, what's the 2 newton force? It is anticlockwise. And the distance from the point is 1 plus 1, 2. So 2 times 2 is 4. So what do you notice?
The result is 7.
The result is 7? Is you sure? What's the total clockwise?
3.
The total clockwise, you've got a 2 plus a 1 is 3, yeah? And the anti-clockwise? 10. Okay, so 10 is the strongest of the 2. It's anti-clockwise, you've got 3. And the clockwise, and so you subtract those 2, get 7. You should see my handwriting using a mouse. It's very, very bad. There you go, that would work in grade 2. Good. So I'll try now the second question. So the first one, you've got correct 7 newton meters in the anti-clockwise. No, I paused my screen. I didn't record all of the handwriting. That's not very sensible. Okay, so the second one. No, the second. Oh, you don't see it. That's right. You don't see it. Yeah, actually, that won't do. Do number 65. F. Yeah. I'll give you a hand with this because you missed the first section. We've got first consider say 5 newton first. So that is 5 times. No, perpendicular distance. That's what we're given to. The distance is. Okay. So you get that, and that's going to be a clockwise distance. So what's that moment? How much is that? Okay, good. So 4 newton meters clockwise. Now this one's a bit more difficult. You've got to actually work out the distance from P directly to the line. And then you use that triangle. The top of that is 2.5 and the angle is 65. Let's wrap this up and record it. All right. So let's have a look at the first force. We've got 5 newtons, and that's going to cause a clockwise or anti-clockwise? Clockwise, good. And its distance away is 0.8. So it's 5 times 0.8, and that gives us 4 Newton meters, yeah? And the other one now, we've got to get the perpendicular distance from P to the line. And so we found the hypotenuse is 2.5. Do we ever use sine or cos to get that perpendicular distance? Yeah, because it's the opposite side from 65. So 2.5 sine of 65 is the distance. So the force is 6 and the distance is 2.5 sine of 65. Have you got a calculator? What did you get?
The final is
13.59, and we'll do 3 significant figures. We'll go 13.6, and that is anticlockwise. See, I still don't know. I've got to actually go through and say, against the clock. And so we've got a stronger force in anticlockwise, small force of 4 in the clockwise. So we'll subtract that 13.6 minus 4 to get 9.6 Newton meters in the anti-clockwise direction. Okay, this third module that we'll is solving a problem, solving the apparatus. So we looked at this learning objective, finding the sum of moments about a force, and we've done 2 types. One is where we have just forces clockwise and negative, and the other is like using a live rod. Solutions. Okay, this learning objective is solving problems with what is at rest. So now it's not going to move clockwise or anti-clockwise. When it's at rest, it means it's equilibrium. And if it's an equilibrium, we know that the vertical equals the horizontal and the anti-clockwise equals the clockwise. Clockwise equals the anti-clockwise for your benefit. So the vertical forces equals the horizontal, and that, if you have a force up of say 10 newtons and a force down of say 12 newtons over here, a force down of say 2 newtons over here, and a force up of some newtons here, you can look at those and say, well, we've got a total force of 12 plus 2, 14 down, 10 plus, so this would have to be. Straight away, we could use this concept vertically with horizontal. The down forces plus the equals the up force. Now the thing with equilibrium is also that the clockwise is going to equal the anti-clockwise. So if we had a situation where we're standing, we've got a force here, and it's like sitting, it's like the legs of a table. We just sort of put legs here, we put the table here. There might be 1 metre to the edge there might be 2 metres to the edge here. And we've got now this is not a light rod, okay? So let's call this not a light rod. It might say a mass and the force times its acceleration now. In the center, if it's a uniform rod, then let's put this as an 8 metre, right? And let's call it 13 Newton force down in the center. 13 newtons down. Now there's a force acting up here from the resistance force of the stand, and there's a force acting up here. And this is at rest. If this is 8 meters long, that's 2, that will be 2, that will be 3, and that would be 1. Now, if I took moments about this point here, let's call that point A and point B. If I took moments, we want to find this one, A newtons. What is that force? What is the resistance? And what is the force? If I took moments about A, because A is 0 meters away, it won't be part of the formula, the equation. So when you take moments about A, that will help us find B. Because 0 times that force is 0. There's no force here. There's a force acting in clockwise of 30 times 2, 60 Newton meters in the clockwise. And there's an anti-clockwise of B acting how far away? From 5 meters. Now they should equal each other because it's at rest. There's no overall. So 30 meters, 30 Newton, 60 Newton meters clockwise, 5B Newton meters anti-clockwise, therefore 5B equals 60. Therefore B will equal 12. Now, 60 Newton meters equals 5B Newton meters. But the thing is, B is the Newton and 5 is the meter. So you've got to realise we're finding B, we're finding a force here. That B value is 12. Yes, up here is 5B Newton meters, but here B is not Newton meters. So just keep, we are finding a distance or we're finding a force, or we're finding a moment, which is Newton meters. Okay, so if we took moments, we could take moments about B, but let's let's just look at what's total up, total down. Total up being 30. So if B is 12, A should be? Yeah, it should be 18. What would we do if we did 30 times 3 anticlockwise? We get 90. This would be 5 times what to get 90? So you could do the same situation. You get 90 Newton meters here, and you have to get 90 Newton meters here. So 5 times what equals 90? 90 divided by 5, you get 80. So it's just as easy to use the 12 plus 18 as it is, it's easier to do that. So let's have a look at a question in your book, and I'm looking specifically at a 20 Newton meter rod, which is, this is 20 Newton meters. It's a uniform rod. So uniform means it's not, the center of gravity is right in the center. Okay, so let's have a look at just two, part B. Try and find the forces at C and D.
Okay, no. Yeah.
So this time we will take moments, choose either to take moments about C or D. If you choose to take moments about C, you will be able to find D. Because D is so many meters away from C. So C becomes your point where you take your moments about. That way we eliminate one of the variables by taking moments. If you took moments about here, you would have a variable B and a variable A, two equations. We try to eliminate that by taking moments about where it's here, we'll take moments about C, and then we've got which forces. You remember the center of gravity? Remember this one? You've got to draw this one in yourself. Okay, this is a 30 Newton not-to-light rod, which means it has a mass, and it's actually right down in the center, 4 meters. So this has a mass of 20 meters. Oh, you've got it done. Okay. So what's your arrow in the center? So in the center, put your arrow down, put a 20 there. It's a total of 5 meter rod, right? So this is a 5 meter rod. It was one here. This would have to be 1. It's a 5 meter rod. That's at 2.5 meter mark. Is this what we're doing? Which one are we doing? Sorry, that's not what we're doing. That's two. Yeah, that would be. Distance is real. So we take moments about C. So this is up. Clockwise or anti-clockwise. And this one will be at D. There's a little triangle at D. This one is of course up. And it won't move. It's not going to push it greater than the mass. But it will provide a force that comes from this. And that will be a force in the anti-clockwise. This is a moment in the clockwise. So your clockwise moments equals, what's your force? From C. Let's take moments from C. So how far away is the center of gravity? 0.5? Good. So we got 2 meters already. Another half a meter if you've got the mass of the rod. And we're told it's a 20 Newton, not a light rod, it's 20 Newtons. 20 in the center. And this distance from C to the is 0.5 because it's 5 meters long. So that moment is 20 times 0.5 equals what? Clockwise or anti-clockwise? C. Now the force up at D is, we don't know, so it's D times, what's our distance? 2, yeah, from C. So our distance from C is 2 meters, so it's D times 2, and that's Newton meters, and that's in the anti-clockwise. So because it's at rest, 10 Newton meters will equal 2D. Therefore D equals, good. So 5 newtons. And now you know it's 5 newtons, we've got 20 newtons. What can you tell us about C? 5 newtons here. That's 20 down. So how much will I take? That's 5. This will be? Down is 20. Up is 20. So down is 20, you've got 5, and you've got another 15. So, sorry, so we've got C is 15 Newton meters up. Oh, sorry, 15 Newton. Okay. All right, there's a second one I'd like you to do on that page, and it is got 1x. Just 15 up, 20 down. 15 up, 20 down. It's this one, our 2-part B. And this rope, it says each of these diagrams shows a light rod. So what does this mean as opposed to 20 newtons? There's no arrow at the center. It's a light rod. We don't have this. It's not a light rod, you'll have an arrow in the center. If it's light, it won't have. It's insignificant. What were you taking moments about initially? Which point? Oh, you're just looking at up equals down. Yeah, yeah, okay.
Oh, it is
No, that's fine. Up equals down. That is an X. Yeah. So up equals down. That doesn't really help us, does it? We've got an X and a Y. So we're going to take moments about. Put your pen at a point where one of the unknowns is. Before we didn't know A, so I started here. We could have started here. The second one, there were two unknown points. That was at C and D. We decided to go and take moments from C or D. So where are you going to take moments from? Which point? Put a point where you're going to take moments from. Well, you know what 15 is already, but that's the wrong point.
X.
Yes, either X or Y. So we're going to take moments from, you'll take moments from here, you're taking moments from X, it's your choice. Now, start from here. This force has, that force is here, and that force is there. So some are clockwise, some are anti-clockwise. The distance from that point. So force times distance, force times distance, force times distance. And know whether if it's anti-clockwise or clockwise. So which one is good? 15 times 2, good, alright, and then is going to be which one? Good, so put C or power like that, clockwise, CL, or good. Yeah, good. Now which one are you going to do? We've done the one. Which one next? Okay. How far away is it? 2, good. So this one, 15 times 2, this one nice, this is 25 times, is equal. Oh yeah, 20 times, yes, good, 60, and that is, which one? Right. And this one was x times how far away? Where is your point? Where are you taking moments from? Do you cancel? Where are you taking moments from? Yeah, the distance from that point. This way.
So, it's you.
Yeah, good luck. Okay. So what are the total clockwises? 30, and that's it. And 30 clockwise. This 30 is clockwise. This is clockwise. So that's 30 plus 1. 30 plus 6. nothing. There's no force. That's y times 0. So y times 0 is 0. There's no moment. So this one is clockwise, this one is clockwise, and only that one is anticlockwise. Yeah. And here will be good. What did you get for y?
35 and 96.
And does that all balance? So we've got 35 going up plus 15, that makes 50. So we've got 20 here, 30 here, 15 here, so all that. Now we've got down, 20 down, 30 down, 15 down, and so that way. Yep. What did we get? 15 plus 5 makes 20. 20 plus 30 makes 50 down. You've got 20 down, 20 down, that makes 50 down. Good. Right, so we join limits about x. And so let's take limits about x, and you'll see you get the simple x times 0 is 0. So if you wanted, you could say there's no clockwise or anti-clockwise, because there's no distance left. This is a clockwise, this is a clockwise, and this is a anti-clockwise. So we've got y times 1. We've got 15 times 3. And we've got 20 times 4, which is anti-clockwise. Thank goodness we've got an OC. Thank you, OC. Therefore, 80 anti-clockwise has to equal the sum of the clockwises, which is 45 plus y. Therefore, y equals 35 units. Then you've got 35 up, 15 up, that makes 50 up, 20 down, therefore 30 down. Okay. Good. So that brings us to the end of. Okay. So with vectors, it's looking at how to use vectors. What is a vector? To describe, yes, displacement. A few things about vectors and scalar. Vectors and scalar quantities. Scalar quantity just says how many, how far. I traveled like 11 kilometers to get here this morning. That's a scalar distance. But if there is, if I get a straight line and measure from where I left to where I am now, despite how far I traveled, from where I started to where I finished in a straight line, that's my displacement. Hello. Wow, welcome. You just walked in at the second session. You just had a break. So good timing. And you can squash up here if you like. There's enough room, so whether you slide over, let's sit in the middle, or whether you can move across a bit more. So just with the computer. Have you got a textbook? I was thinking I was going to talk to myself today. So thank you for showing up, you guys. I'm talking to myself. So we're looking at vectors now. We've just finished this morning looking at the moment, and I'm attempting to record sessions. So what will not be recorded is what you see here, because that's live. That the students who aren't here don't get the benefit of what we're writing on the board. They only get the benefit of listening and looking at the questions, and at the moment we're just recording a blank PowerPoint slide. That's all I want to get to see. When you guys leave for study, I negotiated with Ms. Nish and Ms. Valdina. I think this is going to be possible unless they reschedule my time. When you have maths, I'm going to continue on, and we will, if you wish to, you can log in. And those sessions are actual revision sessions. So some sessions, I will choose a particular aspect to revise, and then give you a chance to, if you want to email me a particular, if you've got a suggestion, then I will run with that whoever says request, and I'll use that request as a 15-minute segment of a session. And I just break them up into 15-minute bite-sized pieces. Vectors has about 7 of these 10 to 15-minute bite-sized pieces. When we finish vectors, we, for those of you who wish to stay, we can continue to go back to what I wanted to do yesterday. I wasn't good to myself yesterday, and I logged in at a time when I was offline. I had so much trouble that yesterday was a learning, just getting familiar with how to run this whole game. I've never done this before. So I've learned from yesterday and from this morning how to video these sessions. The first 10 minutes have to be actually video. Then, so the first section, we're just about to launch. I'm using vectors to describe displacement. The displacement from where I left this morning home to here, a straight line, and the direction, that would be the displacement. You can get that quite easily on Google Maps, draw a straight line and look at the compass direction. The distance and the direction, that becomes displacement. So I might not just 11 kilometers, but like we were talking about, was it anticlockwise? Vectors must say 11 kilometers southwest, or 11 kilometers east. Displacement has a direction. Velocity is a vector quantity. Velocity has a speed and direction. So speed is the scalar part of it, just the magnitude, how big it is. But the direction, so you've got a speed, and you've got a direction, and then you've got a velocity. So what we're going to use vectors are like straight lines, which we use to describe displacement. So I'll start with looking at just moving. Let's say we go 6 kilometers east. So we start here and we go 6 kilometers east, and we stop. Conveniently, we turn and head due south. Conveniently, say 4 kilometers. We head due south. The question is, how far are we away from where we started? And in what direction? So there's 2 things here, is how far, that's distance, and displacement is distance and direction. So displacement equals a distance and direction, not just distance. So we have moved from here, so okay, let's calculate this. How are we going to do this? It's a 90-degree right angle triangle. So we'll just say 6 squared plus 4 squared equals, and whatever our distance is, x squared. A good old Pythagoras student. What did you say?
7.2.
But here x squared equals 52, and x equals root 52, and approximately 7.21 millimeters, 3 significant meters in that distance. And what direction? Now, here if I put it anywhere here, and I use the opposite and adjacent, what ratio 10? 10. So 10 of theta equals opposite over adjacent. Is they don't say inverse 10, they say R10. Okay, so when you're calculating this, do they use it in this chapter? Just say 10 of theta equals, so don't say, what did I see R10? Right, if it is, but at the moment we just say, therefore, theta for that will be 2/3 shift 10 or arc 10, 2/3, so what's that out? I'm going to write it down here anyway because eventually you're going to see this arc 10. 30 point?
33.
38 point?
33.
33 point? 7 degrees. Yeah, that's not 3 degrees. If you wanted a compass direction here, compass direction would be east, north is 0, east is 90, south is 180, and west is 270. If we were to go another 33 degrees, we would have a compass direction of 123 degrees as a compass bearing. 90 is east, so 0 is 1. That's different than the normal 0, 90, 180, 270. Okay, so we've looked at using vectors. A vector is, we can use a line to represent a vector. It has, if you draw it exactly, say 6 centimeters, you can easily draw it to scale. 6 centimeters. Also, if you measure that length, you'll have approximately, say yourself, and just measure and see, so it's a bit more than 7. Okay, there's a question I'd like to look at in the textbook, which is on page 135, and it's a man walks 3 kilometers due east. This is the question that I've got on my slide here. A man walks 3 kilometers due east and then 5 kilometers northeast. Find the distance from the original position. So a diagram is always useful here. So by starting with the diagram, you put a little arrow east, 5, there east, and then you put a little 3 to represent that arrow. And then from there, northeast. So from here, northeast is, there's a little compass. We head in this direction to that point here. Okay, so how far are we from our original position? Now, you know triangles. What is that angle in that triangle? If it's, this is 90 plus another 45 degrees. So we will have 135. We've done sine cos rules. What's What's the cos rule? A squared equals B squared plus C squared minus cos A. In this case, A is 135. B is 3. C is 5. What? No, I didn't expect more.
Yeah.
Okay, so we'll bring this tape out here and you can sit. Just got webcam on, so only for the benefit of if anyone logs in with the webcam, but we're recording the sound and the slides for the benefit of having a record later. If anyone did not show up, they could listen to what we said and follow the questions on the slides. What we've done this morning is looked at, we finished looking at moments. We're looking at now the chapter on vectors. We only really just started. And we're looking at vectors being distance and direction. And our first question was, if we go 6 kilometers east, 4 kilometers south, how far are we away? We use triangles. Here we use Pythagoras. We use 10 to find the area. Now we've got a question in the text on page 170, is it? 135. And during your study leave, when we normally have mathematics, I will be talking to myself again with the computer set up like this, where you will see on the webcam what I'm doing, and I will still run certain module sessions. You will get an email. I'm not sure if anyone have come across those emails. The email gives you the link. There's a bit of a problem. I think the computer still needs to get that software to be able to run. I think it automatically installs that onto the computer. All right, so this question was 135, page 135, question 3. So we went 3 kilometers east, 3 kilometers east, and then went 3 kilometers east, and then 5 kilometers northeast, that's this direction, northeast. How far are we? So from that triangle now, we've got a 135 degrees here. And the trick here was to say, you've got a formula sheet. If you don't know what formula, work with your formula sheets. You had do you have your own copy? Do you have a digital copy? You should. It'd be good to be able to try and make that available. A squared equals 3 squared plus 5 squared minus 2 times 3 times 5, 30 cos 35. Make sure you've got a D on your calculator, please. And then get the square root of that answer. 34 minus 30 cos 135. How did we go? So, let's see if you've got the right number. 34 minus 30 times cos of 135. I've got 34 plus 15 root 2. How do I turn that into a decimal?
55.21%.
What did you get?
55.21.
55.21. So we got? And now the square root of that.
7.43.
7.43. A is approximately 7.43 kilometers. Now the question didn't ask in what direction.
This one bearing.
Oh, bearing does. Okay, fine. It's just and bearing. Bearing is the computer, the calculator, the compass. Bearing is the compass direction. So north is 0, east is 90. This bearing here, from here to here, is on a bearing of 45 degrees. It's actually, bearings are usually in 090, a bearing of 0.45. We want, if you were standing here from the start to the finish with a compass, what is that bearing? Does it say from or to? Okay, it's important to stand where you want to hold the compass. So we want the bearing from here. This is where you would hold the compass. Because if you want the bearing back to where you came from, so the bearing back to your point of view, you have got to stand here, you get a different bearing. 180 degrees difference. So let's look at an angle here, theta. And what rule will we use? Sine. So sine rule says that the side over sine of the angle equals the side 7.43 over the sine of 135. So the side over the sine of the angle opposite. The side over that side over the sine of that angle, that side 3 over the sine of that angle, which we don't need to know. We could have found any one of those. Therefore, what is that angle? We can cross multiply, bring that up 5 times sine of 135 equals 7.43 theta. Divide that by 7.43. And then shift sign. Let's see if you get the same answer. Divide by Did you get an angle of 28 degrees? About 28.2. Okay. So we've got approximately 28.4. Bearings will only have the main, the rounded off to the nearest degree. I think in this book, they just put the bearings rounded up to the nearest degree. That is not the bearing. That is 28 degrees around from east. East is this way, and it's 28 degrees back from east. So what would we do there? Well, east is 90. Come back 28 degrees. You will get the bearing. Because this way is 90, but turn 28 degrees back towards north, you're going back. If you were to go this way, your bearings get larger. It goes from 90 to 180 as you turn south. But 90 east, back 28, you're going back to 0. If you go all the way back to north, you're to 0. Only halfway, you're at 45 degrees. This is parallel to that one there, that direction is 0.5. Not quite, only go back 28 degrees. So we get 62. And being a fussy old pilot man who only flying single engine planes and biggest up, 3 numbers for bearing 062. I'm bearing 062. So we're flying, I'm not on a bearing of 62. On a bearing of 0, 6, So say each number, you don't even say 62. You don't need to know that, right? I bet the book just says 62 degrees. Let's see if it's a mathematician who wrote a pilot. This is question 3, 6A, question 3. Impress me, book, come on. Oh, I'm impressed. I am a happy Vegemite. In Australia, I have to say Vegemite. Okay. Do you know what Vegemite is?
Yeah.
In Australia, I had it for breakfast this morning. My friends came to visit me and they bought 2 jars of Vegemite. Very, very lucky because one just ran out last week. It's black, thick paste.
What should be a Vegemite?
And yeast extract.
Be a Vegemite.
Candy. I think there's a few places that sell it. I think Honey sell it at Jumeirah, and probably Spinneys might sell it. Yeah, Spinneys sell it. Vegemite. But it's much cheaper when it comes in plain and something. Good. So we've looked at the first module, and that is using vectors to describe display sequences. Okay, our next topic we're going to be looking at is the method of adding vectors and using what we've just done, using line segments to represent vectors. My pen is, that's all right because there's only one attending this session, so you guys let me know. I've got another one. Is that all right? Yeah. Okay, a vector line segment. What we got here is in the x and y axis, we've got the origin at 0, 0. Now, any point, if we get a point, say 6, 5, that's the point, that's the position 6, 5. Now, to get to 6, 5, let's call that point P. I will call that little p, and that line there joining from O to P, if it's from the origin, it's got a special name. That vector is called a position vector. Position vector of P. P is a position vector. If you're told that P is a position vector, it means it's going from 0, 0 to the point P. So if I said the vector A is a position vector, where is it coming from and going to? If I said that A is a position vector, where does it start, where does it finish? It'll start at the origin and it'll go to point A. Capital A. So little a represents the vector. And there might be a point A somewhere. A might be here. And this vector going from O to A is vector A. Vector A can be moved anywhere we want it to. We could put vector A over here. We could put vector A